Large language models, attention-based architectures trained on internet-scale data, have demonstrated state-of-the-art reasoning for various language-based tasks. Recent work in the robotics community has sought to translate these successes to robotic tasks. LLMs have been used to generate high-level plans, robot control code, and reward functions. But what if a task is not well contained in textual or even visual inputs? In this work, we are interested in dynamic manipulation tasks. Dynamic manipulation can increase robot workspaces, improve task efficiency, and enable novel skills. However, task outcomes are often tied to physical properties such as friction and mass that are not directly observable in image data. Additionally, these systems have complex dynamics that is unlikely to appear in LLM training data. How then might we exploit pre-trained LLMs for these tasks? The majority of existing work utilizes LLMs via in-weights reasoning. In this operating mode, the LLM is prompted and responds using information stored in the model weights during training. However, LLMs have also been shown to perform in-context learning. With in-context learning, a small number of examples are provided in the prompt of a pre-trained LLM, which learns to few-shot predict the result. In this work, we propose utilizing in-context learning to iteratively improve dynamic manipulation policies. By iteratively interacting with the system, we are able to account for variations in underlying physical parameters, correcting for errors in past attempts. We consider solving a dynamic manipulation task drawn from a task distribution, whose underlying parameters tau reflect the variations of the task. Here we consider 5 tasks over 3 environments, 2 simulated and 1 real. In each task, the goal is to dynamically slide, whip, or roll an object to some goal location. We vary either the physical parameters, such as puck radius and rope length, or we vary the target. In our proposed method, the current policy is executed. We then tokenize the policy and the error and provide each directly into the LLM prompt. We then retrieve a set of policy improvement examples from a small dataset. This dataset is over other tasks drawn from the task distribution and can be constructed by demonstration or using a brute force search. The LLM then few-shot learns to apply the policy improvement to the target task. The LLM responds with the policy delta, which is applied and executed on the system. We show several iterative executions over our target tasks. We find that we can effectively exploit in-context learning to improve our dynamic manipulation policies. In our comparisons to baselines, our iterative in-context approach outperforms alternatives such as random shooting, Bayesian optimization, and fitting the policy improvement using other sample-efficient methods, such as k-nearest neighbors and piecewise linear modeling. Across our tasks, we find our method is able to converge to a policy solution with low error, including on the real robot task.